See this case. So let's suppose that you are given this particular red black tree and now you have to delete 11 from this tree. So tell me which is this particular case, what will be the solution for this? We want to delete 11, which is a black node, and we know if we delete a black node, the black height of the tree will be changed, and we need to balance that, right? So in order to resolve this issue of black height of the tree, what we will do, we want to delete a node 11 whose one child is red. Who will tell me? Yes.
Can you please repeat the question?
You can see the slides. It's written over there, delete 11 from this red black tree. So where is the node 11? You can see. So the node 11 is black in color. And all the deletion properties, the process of deletion says that the black height of the tree should not be changed even after deletion. And in every branch of the tree, we can see the black height is equal to 4, like 15, 6, 3, black, and 3 is also having the sentinel nodes which are black in color. That's why I'm saying that every branch has a black height of 4. So 15, 6, 3, 4 height is 4, 15, 6, 13, 15, 6, 11, then 15, 17, 23, 15, 17, 16, 15, 17, 18. So I have just traversed through the complete tree where you can see in every branch of the tree black height is equal to the number of black nodes in a particular branch of the tree, right, till the leaf node. So from 15 to till the leaf node, if we see 15, 6, 3, and 3 is also having the two sentinel nodes, which are the leaf nodes or the null nodes, and which these nodes are black in color and they are also counted. So we say that the black height, so along this branch, the black height of the tree is equal to 4. But if we delete the node 11, so along this branch, the black height will be reduced to 3. So all this, see, we want to perform the deletion, but the black height of the tree should not be changed. So how we are going to handle this particular violation? How are you going to fix up this violation? So we had discussed one example where I told you that whenever we are deleting a particular node, right, so which is black in color, there is a case if this node has some red child. So if this node has one red child, in that case, after deleting this particular node, that red child takes place of the current node which is being deleted, and we change the color of that node to black. So that means 11 to be deleted is replaced with 7, and we will change the color of 7 to black. So since now after the deletion of 11, 7 will be a black node, so the black height of the tree will remain same even after the deletion of 11 along this particular branch. See this? Got the solution?
Yes, ma'am.
11 node को delete कर दिया, सिर्फ इसी part पे, you just focus on only this part of the subtree where we have 12, 11, 7 and 12, 13, right? In this subtree, we have seen the solution. You can see now the 11 is being replaced with 7 and the color of 7 is being changed to black. Now, even after the deletion, you can see the tree is balanced. That means the black height of the tree is same along this particular branch also, 15, 6, 7, and then the last node, that is nil node, that makes up the black height of this particular branch of the tree equal to 4. Is this clear? Is this example clear?
Yes, ma'am.
वैसे जब तक आप इसके जितने भी केसेस हैं आप डिलीशन के, if you will not remember, you will not be able to discuss the solution, or you will not be able to propose the solution to any kind of deletion. Let's take up another example. Now the tree is changed. Here you can see still we want to delete the 11, but now the 11 when we are deleting, it is not having any of the not null children. Since it is having zero not null children, so that means it is not having any child nodes, it is just having the sentinel nodes, right? So what we will do, we will see the color of its sibling, right? The sibling of 11 is 13, right? So we mark, so the node to be deleted is marked as X, and the node sibling of the node is marked as W. So here we see sibling whose color is black and whose both the children, see 13, does the 13 has any children? Can anyone tell? Is the node 13 is having any children?
No,
only
ma'am.
sentinel.
हाँ
Only sentinel null.
हाँ,
null
तो
node.
बच्चे लेकिन हम जो है सेंटिनल्स को भी चाइल्ड कंसीडर करते हैं. They are, because they are black nodes, they are considered, they are counted. Okay, we can't perform any operation on them, but when we are performing the operations on their parent, they are being counted, right? So here you can see, when we analyze this particular case, the color of the sibling is black and the color of its both the child is black. So the both the sentinel nodes, they are black in color. So when we come across this particular case, this case is being discussed as case number 2. So let's go back so that you can see what is being written in case number 2. Here you see. So what is written? Color W red. What is W over here?
Sibling.
Yes, sibling. So what we have to do in this particular case, case 2 says node X is black, its sibling W is black, and both the children are black. And we have come across this particular case when we are deleting the 11 in that particular tree. So what is the solution? Color the W as red, then set X as X parent. That means now the parent of X becomes the new X. After that, what do? We check. If our new X is red in color, we change its color to black, and that we are done. So what will happen? See, what is the, if we change our, see, since we had deleted the X node, and that is basically the changing the black height of the tree, right? And now after deleting that, on the opposite side, the sibling we have changed the color, and here you see we are changing the position of X. That means now parent node becomes the new X. And if the new X is red in color and we change it to black, since parent is, we are changing the color of the parent, and this is along both the branches, right? So the black height of the tree will be balanced if the new node is red and we change its color to black. एक black हमने left hand side से delete किया, जो सिबलिंग था वो उसका कलर भी हमने ब्लैक से रेड कर दिया, तो दोनों साइड में ब्लैक हाइट जो है अनबैलेंस हो गई. अगर हम उनके पेरेंट को जो रेड था उसको ब्लैक कर देंगे तो दोनों ब्रांचेस में हमारी जो है ब्लैक हाइट बैलेंस हो जाएगी, बिकॉज जो अलोंग बोथ द ब्रांचेस पेरेंट इज कमिंग अप जब हम ट्रैवर्स करते हैं, एंड वी आर डन. बट इफ द पेरेंट इज ऑलरेडी ब्लैक, अगर वो ऑलरेडी ब्लैक है तो इसका मतलब वो तो ऑलरेडी ही काउंट हो रहा है उस ब्रांच में. If it is already being counted, in that case we say that the black height of the tree is still not balanced. So that means अब जो है हमें आगे उसको प्रोसेस और करना पड़ेगा, and we will have to check after making this particular change of making the parent of X as the new X and its color is black, whether we have reached to the case 1, 2, 3 or 4. दोबारा से case 2 भी हो सकता है, दोबारा case 1 भी हो सकता है, case 3 और case 4. So in the next state we may be in, because we are traversing up the tree, so we may come across the any of these cases. See this. So we were discussing about this. So 13 is the sibling, both of it, X is black, W is black, both the children of the W are black. So this is case number 2. So what do? We change the color of 13 to be red, right? It is black in color, so we change the color of 13 to be red, and then we make the parent of X is 12, so X becomes a new parent. So when we take this particular step, as this is the case number 2. So the new updated tree looks like this. We have changed the color of the sibling that was 13 to red, and the parent of x that was 12, it becomes a new x. Now you tell me, see again, if now x is a right child of this particular parent 6, that is red in color, and the sibling of x is w, that is node number 3, right? And again, see, now is which case is this? Isn't it this case again, the case number 2? Sibling is black and both the children of the sibling is black. So what do? We again follow the same procedure, right? So what is the procedure that we are going to follow? We change the color of w to red, and the parent of x becomes the new x. Here you see, we have changed the color of w, that was sibling, node number 3 to red, and the parent of x. Earlier, the node x was 12. Now the parent of x becomes that is node number 6 becomes the new node. So now we see what is the new cause. The sibling of x is 17, but x is red in color. So earlier x was black in color, and now the thing is that x is red in color. So what do? Only thing that we need to do is that change the color of x to black, and we are done with the solution. And after changing the color, see, if the node is red in color, the current node, that is x, is red in color, we just have to change its color, and by changing its color we will be able to balance the black height of the tree. So now we can see 15, 6, 2, black height 4, 15, 6, 3, 4, black height is 4, 15, 6, 12, 13, black height is 4, and 15, 17, 16, 15, 17, 20. Along all the branches of this particular tree, the black height is balanced, and this is equal to 4. If any of these step is not clear what we are doing, just let me know. Only thing is you have to remember the cases. Yes? Any doubts? Yes, please.
No, ma'am.
समझ में आ गया? देखो, केस 2 जो है बिल्कुल सिंपल है, उसमें सब ब्लैक है. ये आपको ऐसे ही याद हो जाना चाहिए. केस 2 में सब ब्लैक है, करंट नोड भी ब्लैक है, सिबलिंग भी ब्लैक है, और सिबलिंग के दोनों बच्चे भी ब्लैक है. और उस केस में आपको सिर्फ इतना करना है कि जो W है उसको, जो सिबलिंग है उसका कलर रेड कर दो, और जो पेरेंट है वो नया एक्स बन जाएगा. नया एक्स बनने के बाद आप देखो, अगर वो जो नया एक्स है वो रेड इन कलर है तो बस उसको कलर ब्लैक कर देना. सो दिस वाज केस ए जो अभी हमने किया है. 6 जो नोड है, दिस इज केस ए, और उससे पहले जो भी हम केसेस कर रहे थे दे वर कमिंग अंडर केस बी. जैसे if our new x is red in color, what do? Change its color to black and we are done. So the final solution we are able to get. And for the B, the previous case that we have seen, इससे पहले जो भी हमने steps लिए थे, they were the B case for this second B. So if our new x is black, decide on which case this. And we had seen in all these cases, again we were coming up with the case number 2. So we were resolving that particular केस, एंड फाइनली वी रीच टू केस नंबर 1, और उसके बाद हमने सिर्फ कलर चेंज कर दिया उसका, एंड वी आर एबल टू गेट द फाइनल सॉल्यूशन आफ्टर द इंसर्शन, एंड वी आर एबल टू बैलेंस द ब्लैक हाइट ऑफ द ट्री. लेट्स टेक अनदर केस नाउ. Now you tell me how to resolve this. We want to again delete 11 from this red black tree, and the right hand side of the tree is valid and unaffected, right? We have. So we are just focusing on the left side of the left branch of this particular tree. The node we want to delete is 11. So what do? 11 is black in color. If it is black in color, then what we will do? Yes, please. अभी हमने किया है ये केस.
हम सिबलिंग को देखें.
हाँ, सिबलिंग क्या है? ब्लैक, और सिबलिंग के दोनों बच्चे भी ब्लैक हैं, राइट? सो व्हाट वी आर गोइंग टू डू, सॉल्यूशन क्या है इसका?
मैम सिबलिंग का कलर रेड कर देंगे.
बिल्कुल, सिबलिंग का कलर रेड कर देंगे, और जो करंट x का पेरेंट है वो नया x बन जाएगा, राइट? सो दिस इज w, दिस इज x, दैट इज डबल ब्लैक नोड जैसे हम बोलते हैं। ये जितने भी हम केसेस जहां जहां पर भी हमारा ब्लैक नोड को हम डिलीट कर रहे हैं, दे आर बेसिकली द डबल ब्लैक नोड केसेस, ओके, राइट? So we have changed the color of the sibling, that was 13 to red, and 12 becomes the new x. अब 12 becomes the new x and its corresponding sibling is red in color. जब उसका sibling red in color है और उसके दोनों children black हैं, then what do we do? Now the sibling is red. Yes, this is case number 1. Node x is black and its sibling w is red. Then what we are supposed to do? Color w as black. 5 का color change करेंगे. Color parent of x is red, right? Parent of x is 10, right? So we will change the color of 10 as red. Then rotate the parent of x. अब रोटेशन किस डायरेक्शन में होगी? अब पेरेंट ऑफ एक्स क्या है? 10, so we will rotate it. And rotation कहाँ है? If x is a left child, no. If x is a right child, yes. So we will do the rotation in the right hand side. So when we do the rotation will be done for the parent node. 10 will be rotated on the right hand side. So in every rotation, I told you, just remember, in every rotation, right? So we are doing the rotation from the parent, right? So the parent becomes child and the child becomes parent, depending upon if the rotation is on the right hand side, the left child becomes the parent, the left child becomes the parent, and if the rotation is on the you can say the left hand side, the right child becomes the parent. In this particular case, since we are going to 12, the current node x is our right child, so we are going to take a rotation on the right hand side. So 5 becomes the new parent. When 5 becomes the new parent, 10 will become its one child, right? So 5 cannot have 3 children, right? Because 3 is also a child, 7 is also a child, and 10 will also become a child. So what do we do? The rules of the rotation says that 5 becomes a parent, 3 will become the left child of 5, and 10 will become the right child of 5, and the 7 will become the left child of the node number 10, right? So this is symmetric rotation. If we would have done it in the opposite way, the same could have happened. So अब जो होगा, 5 is the parent node, 10 is the right child of this node, 3 is the left child of this particular node, and 7 will be the left child of the node number 10. See, after the rotation. After the rotation, we have reached to this particular stage. So now after the rotation, you see x was 12, right? So after this rotation, the size of the tree has changed, right? So now x is 12, w is a sibling, right? Node number 7 becomes the new sibling, and both its children are black. So sibling is black, both its children are black, it becomes case number 2. And case number 2 में हम क्या करते हैं? Sibling का color change कर देते हैं, and the parent of x becomes the new parent. So w, that is node number 7, this will be changed, its color will be changed to red, and 10 becomes the new parent. When 10 becomes the new parent, so now what is x? This is 10, and x is red in color. So here we say, if x is red in color, simply change its color to black, and we have found the solution, and we are able to balance the black height of the tree. So unless you remember the cases that we are coming across, you won't be able to balance the black height of the tree, that which particular kind of your step that we have to take. So whether we have to change the x to the parent of x, or we have to change the, we have to do rotation. Even if we have to do the rotation, whether it is the left rotation or the right rotation, right? So you just have to see. Case 2 is simple, where, or you can say all are black, node x is black, sibling is black, both its children are black, right? And after that, case 3 and 4. In case 3 and case 4, you just have to remember what kind of rotation. If it is right hand child is, if it is a left child, take a left rotation. If it is a right child, take a right rotation. So you just have to remember the cases 3 and 4. So is this step, अब जो है आपको पता है कि जब red है तो red के केस में आपको सिर्फ कलर ही चेंज करना है. अगर if the node x is red in color, you just have to change the color of that particular node. That's it. So nothing else to be done, and the black height is balanced. In case number 1 and 2, we have seen what are the steps we take. Similarly, you take we have come across case number 3 also. So within the tree, see, whenever we are performing the deletion operations, we don't know which kind of case we will come across. So we have to remember and we have to analyze the situation. And in these examples, we have seen it is the sibling that plays a important role. So the color of the sibling and the color of the children of the sibling. So you have to, for learning or remembering this, you should design your own strategy so that you are able to take the right steps for balancing the black height of the tree during the deletion. So if we analyze the deletion, it consists of 2 phases. Time that is taken by the first phase, that is log n, that means during the deletion we are saying, and case 1, 3, 4, they terminate after performing a constant number of color changes. We know all these rotations and change of color, they take unit time, right? So O of 1. Case 2 is the only one in which while loop will be repeated, and then the pointer that moves up the tree. This we have seen with the help of the example, that every time we are executing the case 2, it is moving up. So we are iterating through it, right? So when we are iterating, it may take O log of n time. So the total time which are required for the deletion is O log of n. So these are the references you can go through in order to understand better, or you can say just revise your concept. And you better go through these videos. I have explained the things very precisely to you. If you will listen to these videos again and again and go through the slides along with them, the concepts will be more clear. So I would suggest first you listen to the videos and then you read the book. So because